Bridges are one of the most impressive inventions in human history. Whether they span rivers, valleys, or entire cities, they carry enormous loads day after day. But what keeps them standing? Why don't they collapse under their own weight or the thousands of cars they carry? Today, we'll explore the invisible forces and clever designs that make bridges one of engineering's greatest triumphs. Let's start with the basics. Every bridge deals with two main types of weight: its own weight, called the dead load, and the weight of everything that moves across it, which is the live load. Both of these are pulled downward by gravity, creating forces that the bridge must manage. These forces push, pull, and twist every part of the structure, and how the bridge handles them determines whether it stands strong or fails. To resist all that weight, bridges rely on two main forces: compression and tension. Compression pushes materials together like squeezing a spring. Tension pulls things apart like stretching a rubber band. Every part of a bridge is either being compressed, stretched, or both. And the balance between these forces keeps everything in place. It's like a tug of war happening inside the bridge. If one side overpowers the other, the structure could fail. But if they're balanced correctly, the bridge stays up. The arch bridge is one of the oldest and most beautiful types of bridges. It works almost entirely through compression. The curved shape allows the weight of the load to travel outward and downward along the arch. That force is absorbed by the ground through strong side supports called abutments. Because stone and concrete are excellent at handling compression, arch bridges were ideal long before we had steel or reinforced concrete. Beam bridges are the simplest kind, just a horizontal beam resting on supports at each end. When weight presses down on the middle of the beam, the top of the beam compresses, and the bottom stretches under tension. It's a simple design, but only practical for short distances unless you add extra supports underneath. To span longer distances without adding too much weight, engineers turn to trusses, frameworks made from interconnected triangles. Why triangles? Because they're incredibly stable. Unlike rectangles, triangles won't collapse unless their sides break. In a truss bridge, some beams handle compression while others handle tension, creating a lightweight yet strong structure that efficiently distributes the load. The cantilever bridge is a bit more complex. Picture it like two diving boards reaching out from opposite sides, balancing each other in the middle. These bridges use structures that extend horizontally and support themselves using counterbalancing arms. Some parts are compressed, some are in tension, but together they form a stable, self-supporting span, even over long gaps without central support. Suspension bridges are the kings of long spans. They hang the roadway from massive main cables that stretch between tall towers. The main cables experience tension. They're being pulled tight by the weight of the bridge and traffic. That force transfers into the towers, which are under compression, and then into the ground through solid anchors. This clever distribution of force is what allows suspension bridges to stretch for miles, like the Golden Gate or Brooklyn Bridge. No matter the design, arch, beam, truss, cantilever, or suspension, all bridges rely on the same principles: managing tension and compression, balancing forces, and using the right materials for the right job. Every bridge is a puzzle, solved by engineers who combine physics, math, and creativity to turn ideas into reality. This is Enginuity, where we break down the strength behind engineering. Subscribe for more builds, breakdowns, and big ideas.